Settle into the sleepy mind channel, where tonight we uncover one of history's greatest engineering mysteries. For nearly 1,000 years, a handful of master swordsmiths created blades unlike anything the world had ever seen. Their swords shimmered with flowing patterns that resembled rippling water, held edges so sharp they inspired stories that spread across continents, and possessed an extraordinary balance of strength and flexibility that amazed warriors, rulers, merchants, and travelers alike. These remarkable weapons became known as Damascus steel swords. Even today, despite powerful microscopes, advanced chemistry, and modern metallurgy, scientists still cannot say with complete certainty how the greatest examples were made. Hidden inside every blade was a secret that remained invisible for centuries, waiting patiently for modern science to begin uncovering what ancient craftsmen somehow understood through experience alone. The city of Damascus, located in present-day Syria, became one of the greatest commercial centers of the medieval world. Caravans arrived from Persia, Arabia, India, Egypt, Central Asia, and Europe, carrying silk, spices, precious stones, rare woods, ivory, incense, and valuable metals across thousands of miles of desert and mountain trade routes. Among these countless goods traveled some of the finest steel ever produced, and within the workshops of Damascus, master blacksmiths transformed that steel into blades whose reputation became almost mythical. Although historians now believe the steel itself originated much farther east, especially in southern India and Sri Lanka, the finished swords became so closely associated with Damascus that the city's name would forever become linked with one of history's greatest engineering achievements. What makes this story even more fascinating is that the original method gradually disappeared. The finest Damascus swordsmiths left behind no detailed instruction books, no engineering diagrams, and no scientific explanations describing exactly how their greatest blades were created. Instead, their knowledge passed quietly from master to apprentice across generations, with each craftsman learning through years of observation, repetition, and experience beside the glowing forge. As kingdoms changed, trade routes shifted, and the supply of the remarkable steel they depended upon slowly declined. Much of that specialized knowledge vanished with them. By the 19th century, authentic Damascus steel had largely disappeared from history, leaving behind only surviving swords and centuries of unanswered questions. Today, researchers continue studying these remarkable blades using electron microscopes, X-rays, spectroscopy, and advanced material science, discovering that the ancient craftsmen achieved results far beyond what historians once believed possible. Tonight, we will follow the complete story from beginning to end. Our journey starts not inside a blacksmith's workshop, but deep beneath the Earth's surface, where iron first formed within ancient rocks, long before the first human ever walked the planet. From there, we will witness the discovery of metal itself, the rise of early civilizations, the invention of furnaces capable of producing iron, the extraordinary development of crucible steel in southern India, the busy markets of Damascus, and finally the patient work of master swordsmiths who shaped glowing steel with little more than charcoal, fire, experience, and remarkable skill. Along the way, we will uncover the hidden chemistry of carbon, the microscopic structures locked inside every blade, the science behind their legendary strength, and the beautiful flowing patterns that continue to fascinate historians, engineers, collectors, and metallurgists around the world. If you enjoy relaxing educational sleep stories, Feel free to like and subscribe. New sleep stories are posted every other day. For all night listening, be sure to explore our growing collection of playlists filled with peaceful journeys through history, science, engineering, archaeology, and the natural world. Long before Damascus steel became famous, before merchants carried precious ingots across Asia, before master blacksmiths stood before glowing furnaces, and before powerful kingdoms competed to own these legendary weapons, the ingredients needed to create them already existed deep within our planet. Their story begins more than 4.5 billion years ago, when the young Earth was still a violent world of molten rock, towering volcanoes, and relentless collisions with enormous asteroids. During those chaotic beginnings, immense heat allowed heavier elements, including iron and nickel, to sink toward the planet's center under the force of gravity, forming Earth's enormous metallic core. At the same time, vast quantities of iron remained trapped within the cooling outer crust, locked inside minerals that would eventually become mountains, cliffs, valleys, and rocky hillsides across nearly every continent. Hidden inside those ordinary-looking stones rested one of the most important resources humanity would ever discover. For hundreds of millions of years, those iron-rich rocks remained untouched, while the Earth itself transformed. Oceans formed as the planet gradually cooled. Continents drifted across the surface. Mountain ranges rose before slowly wearing away through wind and rain. Forests spread across the land. Strange prehistoric creatures appeared and disappeared, and eventually, the first human ancestors began walking across landscapes that concealed enormous reserves of iron beneath their feet. Although iron became one of the most abundant metals within the Earth's crust, making up roughly 5% of its composition, it rarely appeared in pure metallic form. Instead, it remained chemically bonded to oxygen inside minerals such as hematite and magnetite. To ancient people searching for food, water, and shelter, these reddish brown and dark black stones looked no different from countless other rocks scattered across the countryside. Yet hidden inside them was a material that would eventually reshape agriculture, architecture, transportation, engineering, warfare, and civilization itself. Before humanity learned how to free iron from those stubborn rocks, people occasionally encountered a very different kind of iron, one that had not come from the Earth at all. Throughout history, meteorites traveled silently through space for billions of years before crashing onto our planet. Unlike ordinary iron ore, many meteorites contained naturally occurring metallic iron mixed with nickel, making them immediately useful without the need for smelting. Ancient civilizations treasured these rare heavenly gifts because the metal could be shaped directly into beads, ceremonial objects, decorative ornaments, and even weapons through careful hammering. Archaeologists have discovered iron beads crafted from meteorites that are more than 5,000 years old, while one of the most famous examples is the beautifully crafted dagger buried alongside the Egyptian pharaoh Tutankhamun. Modern scientific analysis confirmed that its iron originated from a meteorite, meaning the blade was literally forged from material older than the Earth itself. To the people of the ancient world, iron truly seemed to have fallen from the heavens. Meteorites, however, were extraordinarily rare and could never supply enough metal for growing civilizations. If humanity hoped to build stronger tools, more durable farming equipment, larger buildings, and better weapons, another source of iron had to be found. The answer lay inside the ordinary rocks scattered across hillsides and riverbanks, But unlocking that hidden metal would prove far more difficult than anyone could imagine. Unlike copper, which melts at lower temperatures and can sometimes be extracted using relatively simple furnaces, iron demanded far greater heat and far more precise control of fire. Ancient craftsmen faced an enormous challenge. They had to discover how to separate iron from oxygen without understanding chemistry, atoms, or the invisible reactions taking place inside their furnaces. Those discoveries would eventually begin humanity's long journey toward creating an extraordinary materials ever forged by human hands, the legendary Damascus steel sword. The earliest experiments with iron almost certainly looked nothing like the organized blacksmith workshops that would appear centuries later. They were small, smoky, and unpredictable. Somewhere in the ancient Near East, by accident at first, people noticed that certain unusually heavy stones behaved differently when exposed to intense heat inside charcoal fires. These rocks did not simply crack apart like ordinary stone. Something inside them changed. After hours of heating and careful tending, tiny masses of soft metallic iron sometimes appeared among the ash and glowing charcoal. For the first time, people had discovered a way to pull useful metal directly from the earth itself. The process required remarkable patience because ancient furnaces could not completely melt iron. Instead, they produced what modern metallurgists call a bloom, a rough, spongy mass made of metallic iron mixed with ash, charcoal, and glass-like waste material known as slag. Removing those impurities demanded tremendous physical effort. While the bloom remained glowing hot, blacksmiths repeatedly hammered it upon large stones or simple anvils, forcing molten slag from the metal with every powerful strike. Again and again the iron was heated, hammered, folded, and worked until it gradually became denser, stronger, and more useful. Although the craftsmen had no understanding of crystal structures or metallurgy, they were slowly changing the internal structure of the metal itself, improving its strength through little more than observation and experience. This new material quickly transformed everyday life. Stronger farming tools allowed fields to be cultivated more efficiently than ever before. Iron axes cleared forests that bronze tools struggled to cut. Durable plows opened heavier soils, increasing agricultural production and supporting larger populations. Builders shaped stronger chisels for carving stone, while carpenters relied upon tougher nails, saws, and woodworking tools. Entire civilizations expanded because iron made nearly every other task easier. Long before Damascus steel became famous, iron itself had already begun reshaping the course of human history. Yet early iron still possessed significant limitations. Although stronger than many bronze tools, it remained relatively soft and often lost its edge quickly when used for cutting. Swordsmiths could produce serviceable weapons, but the finest blades required something more. They needed a material capable of holding a sharp edge without becoming so brittle that it shattered during battle. Achieving that balance would prove one of the greatest challenges in the history of metallurgy, and the solution depended upon an element so common that few people ever gave it a second thought. That element was carbon. Carbon exists all around us. It forms the foundation of every living organism, appears in charcoal left behind after wood burns, and combines with countless other elements throughout nature. Ancient blacksmiths had no idea what carbon was, yet they unknowingly used it every time they built a charcoal fire. As glowing iron remained surrounded by burning charcoal inside a furnace, tiny carbon atoms slowly migrated into the surface of the metal. This subtle change dramatically altered the iron's properties. Even a relatively small amount of carbon made the metal harder, stronger, and better able to hold a sharp cutting edge. Without realizing it, early smiths had discovered the first step toward making steel. At first, this transformation happened almost entirely by chance. Some pieces of iron absorbed more carbon than others, depending upon the temperature of the fire, the quality of the charcoal, the length of heating, and the movement of air through the furnace. A blacksmith might produce several blades from the same batch of iron, only to find that one performed far better than the rest. Careful craftsmen began paying close attention to these differences. They experimented with longer heating times, different types of charcoal, and subtle changes in furnace design. Over many generations, knowledge accumulated slowly. Every successful blade taught another lesson, while every failure revealed another mistake to avoid. Centuries before scientists understood atoms or chemical reactions, blacksmiths were quietly conducting one of the longest practical experiments in human history, laying the foundation for the remarkable discoveries that would eventually lead to the legendary steel of Damascus. As generations of blacksmiths refined their craft, they gradually discovered that controlling carbon was only part of the challenge. Heat itself possessed an equally important role. Iron behaved differently, depending upon how hot it became, how long it remained at certain temperatures, and how quickly it cooled afterward. Although ancient craftsmen possessed no thermometers, they became astonishingly skilled at judging temperature simply by observing the color of glowing metal. A dull red suggested one range of heat, while brighter orange and yellow indicated much higher temperatures. The forge itself became their measuring instrument, and years of experience taught them how each subtle change in color affected the finished blade. Modern metallurgy has revealed what those craftsmen could never have seen. As iron heats, the atoms inside begin rearranging themselves into different crystal structures. Some arrangements produce softer, more workable metal, while others create harder, stronger steel, capable of holding a razor-sharp edge. Ancient swordsmiths knew nothing about atoms or crystal lattices, yet through countless hours beside the forge, they learned exactly how to guide these invisible transformations. Every successful sword represented not luck, but an extraordinary understanding developed through observation and repetition over many generations. The quality of the charcoal itself also mattered enormously. Not every piece of charcoal burned with the same intensity or produced the same amount of heat. Dense hardwoods generally created hotter, longer-lasting fires than softer woods, allowing furnaces to reach temperatures necessary for working high-quality steel. Charcoal makers became highly respected specialists in their own right, carefully controlling how wood was burned to produce fuel that blacksmiths could depend upon. Long before a swordsmith ever touched a hammer, another craftsman had already contributed to the quality of the finished blade by preparing the charcoal that would fuel the forge. Air proved equally important. A fire cannot burn intensely without oxygen, and ancient blacksmiths quickly learned that forcing additional air into a furnace dramatically increased its temperature. Early bellows, often made from leather stretched over wooden frames, allowed craftsmen to direct a steady stream of air beneath the burning charcoal. With every push and pull, fresh oxygen entered the fire, causing the glowing coals to burn brighter and hotter. Maintaining a steady rhythm on the bellows demanded both strength and endurance. In larger workshops, An apprentice might spend hours doing little else, understanding that the success of the entire operation depended upon keeping the fire alive at exactly the right intensity. As furnace technology improved, so too did humanity's ability to produce increasingly sophisticated forms of steel. Blacksmiths discovered that repeatedly heating and forging the metal removed impurities while improving its internal structure. They learned that some pieces of iron responded differently than others, even when produced inside the same furnace. Certain batches became exceptionally hard after cooling, while others remained softer and easier to shape. Without realizing it, they were observing small differences in carbon content, trace elements, and microscopic structures that modern materials scientists continue studying today. By the beginning of the Iron Age, iron had become one of civilization's most valuable resources. Kingdoms depended upon it for farming, construction, transportation, and defense. Control of iron production often meant economic strength and military advantage. Entire industries developed around mining ore, producing charcoal, operating furnaces, and forging finished tools. Communities grew around deposits of high-quality iron ore, while trade routes expanded to carry finished metal products across increasingly distant regions. Iron was no longer simply another useful material. It had become one of the foundations upon which powerful civilizations were built. Yet despite these remarkable advances, the finest steel in the world had still not been created. Blacksmiths could forge reliable tools and sturdy weapons, but the legendary combination of beauty, flexibility, and extraordinary cutting ability that would one day define Damascus steel remained centuries away. The next great breakthrough would not occur in the bustling cities of the Middle East or among the growing kingdoms of Europe. Instead, it would emerge thousands of miles farther east, in the workshops of southern India, where skilled metalworkers developed an entirely new way of producing steel. Their discovery would eventually travel across mountains, deserts, and seas before reaching Damascus, where history's most famous swords would finally take shape. Southern India possessed something few other regions in the ancient world could match: an extraordinary combination of rich iron ore, dense forests capable of producing abundant charcoal, generations of highly skilled metal workers, and a tradition of experimentation that steadily pushed the boundaries of metallurgy. Long before Europe entered the Middle Ages, Indian craftsmen had already developed techniques for producing steel of exceptional purity and consistency. Their work attracted merchants from across Asia and the Middle East, who quickly recognized that this remarkable material possessed qualities unlike ordinary iron. The steel became known as wootz, a name believed to have evolved from local words describing the material itself. Unlike bloomery iron, which emerged from furnaces as a spongy mass, requiring extensive hammering to remove impurities, wootz steel followed an entirely different path. Skilled craftsmen selected pieces of nearly pure iron before placing them inside small, sealed clay crucibles, together with charcoal and, in some cases, small amounts of plant materials or leaves that may have contributed additional carbon. The crucibles were then heated inside specially designed furnaces until temperatures exceeded anything required by earlier ironworking methods. For many hours, the contents remained sealed from the outside air, while remarkable chemical transformations quietly unfolded inside. Within those glowing clay containers, the iron slowly absorbed carbon from the surrounding charcoal until it reached a concentration far higher than ordinary wrought iron. Eventually, the metal became fully molten, allowing impurities to separate naturally, while the carbon distributed itself far more evenly throughout the liquid steel. This represented one of the greatest technological advances in ancient metallurgy. Instead of repeatedly forging impure iron into better metal, Indian craftsmen were creating an exceptionally clean and uniform steel from the very beginning. Once the crucibles cooled, each contained a small steel ingot that appeared relatively ordinary on the outside, but possessed extraordinary qualities hidden within its microscopic structure. Modern metallurgists have studied surviving wootz ingots with enormous interest because they reveal just how sophisticated this ancient process truly was. The sealed crucibles protected the molten steel from unwanted contamination while allowing craftsmen to control carbon levels with precision. Trace elements naturally present within certain Indian iron ores, including tiny amounts of vanadium, chromium, molybdenum, and other metals, may also have contributed to the unique internal structure that later developed inside Damascus blades. Although the ancient smiths had no knowledge of the periodic table, they understood through experience that certain ores consistently produced superior steel, and they carefully sought out those valuable sources year after year. Producing each ingot demanded extraordinary patience. If the furnace became too cool, the iron would never fully melt. If it became too hot, the crucibles themselves could crack, destroying many hours of careful work. Cooling proved equally important. Rather than removing the glowing crucibles immediately, craftsmen often allowed them to cool very slowly inside the furnace. This gradual cooling encouraged the steel to develop internal structures that would later play a crucial role during forging. Every stage required careful attention because mistakes made during the creation of the ingot could never be corrected once the steel reached the swordsmith's workshop. When the finished crucibles were finally broken open, each yielded a compact steel cake, weighing only a few pounds. These ingots were valuable enough to travel thousands of miles across some of the busiest trade routes in the ancient world. Merchants loaded them onto pack animals that crossed rugged mountain passes, vast deserts, and fertile river valleys before eventually reaching Persia, the Arabian Peninsula, and the thriving commercial city of Damascus. There, master swordsmiths eagerly purchased the precious steel, knowing they possessed a material unlike anything produced locally. The remarkable reputation of Damascus steel therefore began not with the forging of the sword itself, but with these carefully crafted ingots, whose journey had already carried them across much of Asia. The long voyage from southern India to Damascus also protected the secrecy of the process. Few swordsmiths ever witnessed the steel being produced inside its original crucibles, and fewer still understood exactly why it behaved so differently beneath the hammer. They knew only that certain ingots consistently produced exceptional blades when treated with patience and skill. As generations passed, the production of wootz steel remained concentrated among relatively small groups of highly experienced craftsmen, while the art of forging those ingots into legendary swords developed within an entirely different community thousands of miles away. Together, these two traditions formed one of history's most remarkable partnerships, combining the science of extraordinary steelmaking with the artistry of master swordsmiths to create blades whose reputation would endure for centuries. By the time those valuable ingots reached Damascus, their journey had already covered thousands of miles. They had traveled aboard merchant caravans that crossed the Indian subcontinent, climbed rugged mountain passes, followed ancient river valleys, and threaded their way across the vast network of trade routes connecting Asia with the Middle East. These routes carried far more than steel. Silk from China, spices from India, frankincense from Arabia, glass from Egypt, and precious textiles from Persia, all moved together through an interconnected commercial world that stretched across continents. Damascus stood at the very center of this network, making it one of the busiest and wealthiest cities of its time. For centuries, Damascus had occupied an ideal geographic position. Located between the Mediterranean Sea and the great caravan routes leading eastward, the city became a meeting place for merchants speaking dozens of different languages. Travelers arriving through its gates encountered crowded marketplaces filled with exotic goods from distant civilizations. The air carried the scent of spices, leather, incense, and freshly worked wood, while craftsmen hammered copper, shaped glass, dyed fabrics, and forged metal inside workshops that lined the narrow streets. Wealth flowed into the city from every direction, allowing skilled artisans to specialize in crafts that demanded years, sometimes decades, of dedicated practice. Among the most respected of these craftsmen were the swordsmiths. Their workshops were often modest in appearance, yet inside them, generations of accumulated knowledge quietly shaped some of the finest weapons ever produced. Apprentices usually began learning at a young age, spending years performing simple tasks before ever being trusted to work directly with valuable steel. They swept floors, tended charcoal fires, operated heavy bellows, organized tools, and carefully observed every movement made by the master smith. Slowly they learned that forging an exceptional blade required far more than strength. It demanded patience, discipline, observation, and an intimate understanding of how steel responded to every strike of the hammer. When a shipment of wootz ingots finally arrived, the master swordsmith inspected each one carefully before beginning work. The ingots represented a considerable investment, and every piece of steel was treated with enormous respect. Unlike ordinary iron, wootz steel could not simply be heated to any temperature and forged without consequence. Long before science explained why, experienced craftsmen understood that this steel demanded a gentler and more deliberate approach. The first stage involved heating the ingot slowly inside the charcoal forge. This process required tremendous concentration because temperature control proved absolutely critical. If the steel remained too cool, it resisted shaping and could crack beneath the hammer. If it became too hot, something equally damaging occurred. The internal arrangement of carbon-rich structures that had formed during the slow cooling of the crucible could begin dissolving back into the surrounding steel. Once lost, those delicate patterns could never be fully restored. Modern metallurgists now understand this process in terms of crystal structures and carbon diffusion, but the ancient smiths recognized it simply through experience. They knew that overheating the steel ruined its finest qualities, even if they could not explain the invisible changes taking place inside. Once the ingot reached the proper temperature, forging began with slow, measured hammer blows rather than violent strikes. The goal was not simply to flatten the metal, but to encourage it to stretch gradually into the shape of a blade while preserving its unique internal structure. After a period of hammering, the steel returned to the fire for reheating before the process repeated again. Hour after hour, and sometimes day after day, the blade slowly lengthened as the swordsmith carefully balanced force with restraint. Every stage demanded complete attention because a single mistake might waste months of preparation that had begun thousands of miles away in the crucible workshops of southern India. Modern researchers often compare this process to guiding rather than forcing the steel. Instead of overwhelming the material with excessive heat or heavy blows, the smith worked with its natural behavior, allowing the metal to reveal its greatest qualities through careful handling. It was an approach built entirely upon observation. Every experienced craftsman developed an almost instinctive understanding of the forge, recognizing subtle changes in the color of the glowing steel, the sound of each hammer strike, and the feel of the blade beneath the tools. As the blade gradually approached its final shape, another remarkable feature began preparing to reveal itself. Hidden beneath the surface, microscopic bands of carbon-rich material had survived every stage of forging. They remained invisible, while the steel was rough and unfinished, waiting for the careful polishing and final treatments that would eventually expose the famous flowing patterns resembling moving water. Those beautiful designs were not carved, painted, or engraved onto the blade. They had formed naturally inside the steel itself, quietly recording every stage of its extraordinary journey from molten crucible to master swordsmith's anvil. Once the blade had been forged into its final form, the work was still far from complete. In many respects, some of the most important steps had only just begun. The sword now possessed its overall shape, but its ultimate performance depended upon how the steel was treated during the careful stages of hardening and tempering. These processes would determine whether the blade became a legendary weapon capable of surviving years of use, or an ordinary sword destined to chip, bend, or break. Ancient swordsmiths understood that forging created the blade's body, but heat treatment gave it its character. The hardening process required heating the finished blade to a carefully judged temperature before cooling it rapidly in a selected liquid. Modern metallurgy explains that rapid cooling traps carbon atoms inside the iron's crystal structure, creating an exceptionally hard form of steel known as martensite. The ancient swordsmiths knew nothing of crystal lattices or microscopic transformations, yet they recognized through long experience that the speed of cooling dramatically changed the blade's behavior. Too slow, and the edge remained soft. Too fast, and the entire sword risked becoming dangerously brittle. A blade hardened to its maximum potential presented another challenge. Although incredibly hard, it could also shatter under heavy impact if left in that condition. To solve this problem, blacksmiths performed a second operation, known today as tempering. The sword was reheated gently to a much lower temperature before being allowed to cool once again. This seemingly simple step relieved internal stresses that had developed during hardening while preserving most of the blade's hardness. The result was a remarkable balance between strength and flexibility, allowing the sword to absorb powerful blows without snapping while still maintaining an exceptionally sharp, cutting edge. Experienced craftsmen judged these temperatures not with instruments, but with their own eyes. As polished steel warmed, thin oxide layers formed across its surface, reflecting beautiful colors that changed gradually with increasing heat. Pale straw yellow gave way to deeper gold, then bronze, purple, and finally shades of blue. Each color represented a different temperature range and therefore a different balance between hardness and toughness. Master swordsmiths learned to recognize these subtle transitions with astonishing precision. Long before thermometers or scientific laboratories existed, they were using the colors of heated steel as one of history's earliest practical temperature guides. The grinding and polishing that followed demanded just as much patience as the forging itself. Large grinding stones shaped the blade with increasing precision before progressively finer abrasives smoothed the surface until it reflected light, almost like a mirror. Every small scratch left behind by a coarser stone had to be removed before moving to the next stage. This careful progression often required many hours of steady work, yet it prepared the blade for remarkable moments in the entire process. Only after the steel had been polished to an exceptionally fine finish could its famous internal patterns finally emerge. To reveal those patterns, the surface of the blade was treated with mild acidic solutions that reacted differently with the various microscopic structures hidden inside the steel. Regions containing higher concentrations of carbon resisted the reaction differently than surrounding areas, gradually revealing the beautiful flowing designs that gave Damascus steel its unmistakable appearance. The rippling lines seemed almost alive as they curved gently across the blade like moving water, drifting clouds, or the grain of finely polished wood. Every sword displayed its own unique pattern because no two ingots developed exactly the same internal structure during their creation. Much like fingerprints, each blade possessed an appearance entirely its own. Modern research has revealed something far more remarkable. The flowing patterns actually reflected the blade's internal structure, providing visible evidence of the extraordinary metallurgy hidden beneath the polished surface. The beauty of Damascus steel was therefore inseparable from its performance. The same microscopic structures that created the famous flowing pattern also contributed to the remarkable qualities that made these swords legendary throughout the ancient world. The extraordinary performance of Damascus steel soon became the subject of admiration throughout the medieval world. Merchants carried stories of these remarkable swords wherever they traveled, while soldiers who encountered them on the battlefield often described blades unlike any they had ever seen. Some accounts claimed the swords could slice through lesser weapons without damaging their own edges. Others spoke of blades that remained sharp after countless battles or flexed dramatically before returning to their original shape. Like many stories passed from one traveler to another, some descriptions undoubtedly became exaggerated over time, yet beneath the legends rested a genuine truth. Damascus steel represented one of the finest materials that ancient metallurgy had ever produced. Historians have long debated which stories reflected reality and which grew larger with every retelling. Medieval writers occasionally described Damascus swords cutting silk scarves drifting through the air or slicing effortlessly through iron helmets. While such dramatic demonstrations almost certainly became embellished over centuries, careful scientific testing has shown that authentic Damascus blades truly possessed exceptional cutting ability when compared with many other swords of the same period. Their success did not come from magic or mysterious powers. It came from an extraordinary balance between hardness, toughness, and careful craftsmanship that allowed the edge to remain sharp while the blade itself resisted breaking during heavy use. The swords also reflected enormous economic value. Producing one required months of coordinated effort stretching across thousands of miles. Miners first extracted the iron ore. Skilled workers transformed wood into charcoal. Indian craftsmen carefully produced the crucible steel ingots. Merchants transported those ingots across deserts and mountain ranges before they finally reached Damascus. There, master swordsmiths spent weeks or even months forging, hardening, tempering, grinding, polishing, and finishing each blade by hand. Every stage demanded specialized knowledge acquired through years of experience. By the time a completed sword reached its owner, It represented the combined work of countless individuals whose contributions stretched across much of the known world. Because of this immense investment, Damascus swords became prized possessions rather than ordinary weapons. Wealthy rulers commissioned them as symbols of authority, accomplished military leaders carried them into battle, and noble families often passed exceptional blades from one generation to the next. Some swords became treasured diplomatic gifts exchanged between kingdoms, demonstrating respect, friendship, or political alliance. Others entered royal collections, where they remained preserved for centuries. Their value extended far beyond their usefulness in combat. The swordsmiths themselves enjoyed tremendous respect within their communities. Becoming a master required decades of dedication, and only a small number ever reached the level necessary to produce truly exceptional blades. Apprentices often spent many years performing simple tasks before they were allowed to shape valuable steel themselves. They learned how to prepare charcoal, maintain the forge, operate the bellows, recognize subtle changes in heated metal, and care for expensive tools long before they attempted forging their first sword. Many workshops guarded their methods with extraordinary secrecy. Recipes for preparing furnaces, preferred forging temperatures, heat treatment techniques, and finishing procedures were closely protected within individual families or guilds. This secrecy helped preserve a workshop's reputation while ensuring that valuable knowledge remained within trusted hands. A family's livelihood depended upon producing blades that competitors could not easily duplicate. Modern historians believe this secrecy contributed to the eventual disappearance of authentic Damascus steel. As political instability disrupted trade, the supply of high-quality wootz steel declined, and master swordsmiths gradually disappeared without fully passing every detail of their craft to the next generation. By the late 18th and early 19th centuries, the chain of knowledge had largely been broken. The legendary swords remained, but the complete process used to create the finest examples slowly faded into history. Today, surviving Damascus blades are preserved in museums and private collections around the world, where they continue attracting the attention of historians, engineers, metallurgists, and archaeologists. Every sword offers another opportunity to study one of history's greatest technological achievements. Using instruments capable of magnifying steel thousands of times beyond what the human eye can see, researchers continue uncovering new details hidden inside these remarkable weapons. Every discovery brings us slightly closer to understanding how ancient craftsmen accomplished something so extraordinary, while also reminding us that even the most advanced technology of the modern world still has much to learn from the patient observations of skilled artisans who lived nearly 1,000 years ago. For much of the 20th century, many researchers believed the mystery of Damascus steel had already been solved. They assumed the legendary blades were simply examples of exceptionally well-made, high-carbon steel, produced by highly skilled blacksmiths using techniques that had gradually been forgotten. While that explanation accounted for part of the story, it failed to explain why authentic Damascus blades displayed such distinctive flowing patterns, or why their internal structure appeared so different from ordinary steel produced during the same period. As scientific instruments became increasingly sophisticated, researchers began looking much deeper beneath the polished surface, and what they discovered surprised even the world's leading metallurgists. One of the most important breakthroughs came with the development of powerful electron microscopes capable of magnifying materials hundreds of thousands of times. Unlike traditional optical microscopes, which rely upon visible light, electron microscopes use beams of electrons to reveal structures far smaller than the wavelength of light itself. Suddenly, scientists could examine the internal arrangement of ancient Damascus steel with precision. Features that had remained completely invisible for centuries now appeared in astonishing detail, revealing an intricate world of microscopic carbides, crystal boundaries, and complex patterns formed during the steel's original manufacture. Among the most fascinating discoveries were tiny bands of iron carbide distributed throughout the steel. Iron carbide, sometimes called cementite, is an extremely hard compound formed when iron combines with carbon under the proper conditions. Rather than appearing randomly, these carbide particles often organize themselves into long, gently curving bands that followed the famous flow-in patterns visible on the surface of the blade. These hard regions contributed significantly to the sword's remarkable ability to maintain a sharp cutting edge, while the surrounding steel remained tough enough to resist cracking during use. Beauty and performance were not separate characteristics. They emerged from the very same internal structure. Carbon content had to remain within a relatively narrow range. The original wootz ingot needed to cool slowly enough for microscopic carbide networks to begin forming. During forging, temperatures had to remain controlled, so those delicate structures survived instead of dissolving back into the surrounding steel. Even small mistakes could permanently alter the finished blade. Every stage depended upon preserving patterns that the swordsmiths themselves could never actually see. This realization gave historians a new appreciation for the astonishing skill of those ancient craftsmen. They had been manipulating microscopic structures nearly 1,000 years before anyone understood that such structures even existed. Every decision they made, how long to heat the steel, how firmly to strike the hammer, when to stop forging, how slowly to cool the blade, influenced features measured today in millionths of a meter. Researchers also began investigating the chemical composition of surviving Damascus swords with increasingly sensitive instruments capable of detecting trace elements present in incredibly small quantities. Some authentic blades contained minute amounts of vanadium, chromium, manganese, cobalt, nickel, and molybdenum, elements naturally present within certain Indian iron ores. Although these trace elements existed in tiny concentrations, they may have influenced the formation of the remarkable carbide structures that distinguish the finest Damascus steel. Their presence suggested that geography itself played an important role. The quality of the original ore may have contributed just as much as the skill of the blacksmith. This helps explain why modern attempts to reproduce authentic Damascus steel have proven so challenging. A skilled blacksmith can certainly recreate the beautiful flowing appearance using modern pattern welded techniques, and many contemporary blades display stunning visual patterns inspired by historical Damascus swords. However, reproducing the exact internal structure of the finest original blades requires far more than copying their appearance. It demands steel with the proper chemistry, controlled carbon levels, specific trace elements, precise forging temperatures, and heat treatments that preserve microscopic carbide networks throughout the finished blade. Recreating every one of those conditions simultaneously has proven extraordinarily difficult, even with today's advanced technology. As a result, the legendary Damascus sword continues occupying a unique place in both history and modern materials science. It serves as a reminder that technological progress does not always move in a straight line. The Damascus sword therefore represents more than a remarkable weapon. It stands as evidence that observation, practical experience, and centuries of refinement allowed early metallurgists to accomplish feats that continue challenging scientists and engineers even in the modern age. The influence of Damascus steel reached far beyond the workshops where the swords themselves were forged. As knowledge of these remarkable blades spread across Europe, Asia, and the Middle East, blacksmiths everywhere began searching for ways to reproduce their legendary qualities. Some experimented with different types of iron ore. Others modified furnace designs, altered forging temperatures, or developed entirely new heat treatment techniques. Although many succeeded in producing excellent swords of their own, the finest Damascus blades continued occupying a class almost entirely by themselves. Their reputation inspired centuries of experimentation that ultimately advanced the broader science of metallurgy far beyond the original workshops where the tradition began. Europe, in particular, became fascinated with these legendary weapons during the Crusades. Knights returning from campaigns in the Eastern Mediterranean brought home stories describing swords unlike anything they had previously encountered. Some carried captured blades as valuable trophies, while others commissioned local craftsmen to imitate the beautiful flowing patterns that decorated authentic Damascus steel. European swordsmiths were already highly skilled, producing excellent weapons from their own traditions of steel making. Yet they recognized that the finest Damascus swords displayed characteristics they could not easily explain or reproduce. This curiosity encouraged generations of craftsmen to study foreign techniques more closely, gradually exchanging ideas that benefited metallurgy across many different cultures. The blades also demonstrated how knowledge often travels alongside commerce. Without the vast trade networks connecting southern India to Persia and Damascus, the remarkable wootz steel ingots might never have reached the workshops capable of transforming them into legendary swords. Merchants, sailors, camel drivers, translators, and traders all became part of a much larger story. They did not forge the blades themselves, yet their efforts carried both materials and ideas across thousands of miles. Modern historians sometimes describe Damascus steel as one of history's earliest examples of global manufacturing. The iron ore originated in one region, the crucible steel developed in another, the swordsmiths perfected their craft in a third, and the finished weapons eventually found owners across Europe, North Africa, and Asia. Every completed sword represented an international collaboration, centuries before the modern world became interconnected through railways, steamships, and airplanes. Long-distance trade made the legendary blades possible, demonstrating that technological progress has often depended upon cooperation between distant cultures rather than isolated invention. As scientific understanding continued expanding during the 20th century, researchers also became interested in the remarkable efficiency of the ancient manufacturing process itself. Every stage depended upon renewable charcoal, selected natural materials, and an intimate understanding of heat developed entirely through observation. Although modern steel mills produce millions of tons of steel every year with astonishing consistency, they also rely upon vast industrial systems unimaginable to ancient blacksmiths. The Damascus sword reminds us that remarkable engineering achievements can emerge from relatively simple tools when guided by exceptional skill and patience. Conservation scientists now face a different challenge, preserving the surviving blades for future generations. Steel, despite its strength, remains vulnerable to corrosion when exposed to moisture and oxygen over long periods. Museums therefore maintain controlled environments where temperature and humidity remain stable throughout the year. Specialists inspect the blades regularly, removing contaminants with extraordinary care, while avoiding any treatment that might damage the original surface or the famous flowing patterns. Every surviving sword represents an irreplaceable historical document, carrying within it steel information that researchers continue studying more than 800 years after it was forged. New analytical techniques continue revealing surprising details hidden inside these remarkable weapons. Three-dimensional imaging allows scientists to examine internal structures without cutting the blades apart. X-ray diffraction identifies the arrangement of atoms within different regions of the steel. High-resolution chemical mapping traces the distribution of carbon and trace elements across microscopic distances. In many respects, the swords continue teaching modern science long after the original workshops have disappeared. That is a remarkable aspect of the Damascus steel story. It reminds us that knowledge can be both accumulated and lost. Entire generations devoted their lives to perfecting techniques that gradually disappeared as political boundaries shifted, trade routes changed, and essential materials became unavailable. Yet the surviving blades preserved enough evidence to allow future generations to begin piecing together that forgotten knowledge once again. The search for the lost secrets of Damascus steel has inspired generations of modern blacksmiths, metallurgists, engineers, and historians. Throughout the 20th century, countless researchers attempted to recreate the legendary blades using every technique available to them. Some carefully followed surviving historical descriptions. Others analyzed museum specimens in microscopic detail before reproducing ancient furnaces and forging methods as faithfully as possible. Every experiment revealed another piece of the puzzle, yet each also demonstrated how remarkably complex the original process truly had been. Producing steel that looked similar proved relatively straightforward. Producing steel that behaved exactly like the finest historical examples remained an entirely different challenge. One source of confusion came from the modern use of the term Damascus steel itself. Today, many beautifully crafted knives and swords are marketed as Damascus because they display the familiar flowing surface patterns associated with the ancient blades. Most of these modern examples are created through a technique known as pattern welding, in which layers of different steels are repeatedly folded, forged together, and twisted before the finished blade is polished and etched. The resulting patterns are strikingly beautiful and require exceptional craftsmanship, but they are fundamentally different from the original Damascus swords produced from ancient wootz steel. The historical blades developed their patterns naturally from the internal structure of a single steel ingot, while modern pattern, welded steel blades create similar visual effects by combining multiple layers of different steels. Pattern welding itself has an impressive history stretching back many centuries. Long before authentic Damascus swords reached their greatest fame, blacksmiths in Northern Europe had already learned to weld strips of iron and steel together to improve both strength and flexibility. Viking swordsmiths became especially skilled at this technique, producing blades whose twisting internal layers created attractive decorative patterns while helping compensate for the inconsistent quality of early iron. Although these Viking swords and the later Damascus blades often appear similar at first glance, they represent two very different technological traditions that happen to produce surfaces with comparable flowing designs through entirely different methods. Understanding this distinction has become important for historians because it highlights the remarkable sophistication of the original Damascus process. Ancient swordsmiths, working with wootz steel, did not create their famous patterns by stacking different metals together. Instead, the designs emerged naturally from the behavior of carbon and iron inside a single piece of carefully prepared steel. Every wave, curve, and ripple reflected microscopic changes that had begun forming while the steel cooled inside its original crucible in southern India. The beauty visible on the finished blade therefore represented a direct expression of the material's internal structure rather than decoration added during forging. Modern experimental archaeologists have devoted decades to reconstructing every stage of this ancient manufacturing process. Some researchers build furnaces using only historically accurate materials before producing charcoal by hand and smelting iron with traditional techniques. Others recreate ancient crucibles based upon archaeological discoveries, attempting to duplicate the conditions under which authentic wootz steel first formed. These experiments require enormous patience because even small differences in ore composition, charcoal quality, furnace temperature, or cooling rates can dramatically change the final result. These investigations have revealed another fascinating lesson. Ancient craftsmen often achieved precision without realizing they were doing so. Modern laboratories measure temperatures to fractions of a degree, analyze trace elements measured in parts per million, and observe microscopic structures invisible to the human eye. The original swordsmiths possessed none of these tools. Instead, they relied upon memory, observation, and an intimate familiarity with their materials developed through years of daily practice. Their knowledge existed not inside books, but inside their hands, their eyes, and their accumulated experience beside the forge. This realization has reshaped the way historians view many ancient technologies. Damascus steel stands among the finest examples of this process. By the time the greatest Damascus blades were being forged, the knowledge embodied within each workshop represented hundreds of years of accumulated observation, even though very little of it had ever been written down. Today, when visitors stand before an authentic Damascus sword displayed inside a museum, they often admire its graceful shape and beautiful flowing patterns without realizing how much history rests within the steel itself. The blade tells the story of ancient geology that created the iron ore, the forests that supplied charcoal, the crucible makers of southern India, the merchants who carried valuable ingots across Asia, the bustling workshops of Damascus, and the master swordsmith who patiently guided every stage of forging with little more than experience and observation. Few objects preserve such a remarkable combination of science, engineering, commerce, artistry, and history within a single piece of metal, making the Damascus sword an extraordinary achievement of the ancient world. The legacy of Damascus steel extends well beyond the swords themselves. Although modern alloys are produced using computers, precision furnaces, and controlled industrial processes, the fundamental question remains remarkably similar to the one ancient swordsmiths faced centuries ago. How can the internal structure of a material be controlled to produce the best possible performance? The Damascus sword represents one of humanity's earliest and most successful attempts to answer that question. Modern steel production operates on an enormous scale compared with the quiet workshops of medieval Damascus. Giant blast furnaces transform millions of tons of iron ore into steel every year, while continuous casting machines shape glowing metal into massive beams, rails, and sheets destined for construction, transportation, and manufacturing around the world. Sophisticated laboratories monitor chemical composition to astonishing levels of precision, often measuring individual elements in concentrations of only a few parts per million. Yet despite these extraordinary technological advances, engineers still rely upon the same fundamental relationship between iron, carbon, heat, and cooling that ancient blacksmiths gradually uncovered through centuries of observation. The study of ancient Damascus steel has also contributed to a broader understanding of how materials behave at the microscopic level. Researchers now recognize that tiny changes in grain size, crystal structure, and the distribution of carbon-rich compounds can dramatically alter the properties of an entire piece of steel. A blade may appear perfectly ordinary to the human eye, while containing an incredibly complex internal landscape visible only under powerful microscopes. Every crystal boundary, every carbide particle, and every microscopic layer contributes to the finished material's strength and durability. This realization has become one of the cornerstones of modern metallurgy, influencing the design of advanced steels used in bridges, automobiles, spacecraft, and countless other technologies. The Damascus sword also demonstrates the remarkable importance of controlling temperature throughout manufacturing. Modern industries invest enormous effort in precisely regulating heating and cooling, because engineers understand that even small differences can dramatically affect a material's final properties. Computer-controlled furnaces now perform heat treatments with extraordinary accuracy, yet the basic principles remain unchanged from those practiced centuries ago. Steel must be heated to the proper temperature, held there for the correct amount of time, and cooled at controlled rates to produce the desired internal structure. The ancient swordsmiths could not explain these transformations scientifically, but they mastered them through experience with astonishing success. Another lesson hidden within the story involves the value of interdisciplinary knowledge. The creation of an authentic Damascus blade required expertise in geology, mining, forestry, charcoal production, ceramics, metallurgy, blacksmithing, commerce, and transportation. No single craftsman controlled every stage of the process. The finished sword therefore represented the combined achievements of many different professions working together across thousands of miles. Today we often describe this type of collaboration as a supply chain, yet the principle is far older than the modern industrial world. Historians also point to Damascus steel as an excellent example of technological knowledge depending upon stable societies and reliable trade. The remarkable wootz steel produced in southern India reached Damascus only because merchants could travel safely across long-established commercial routes linking distant civilizations. When wars, political upheaval, and economic changes gradually disrupted those connections, the flow of crucible steel slowed and eventually disappeared. Without access to the original material, even the finest swordsmiths could no longer continue the tradition exactly as their predecessors had. The disappearance of Damascus steel therefore reminds us that technological achievements often depend not only upon invention, but also upon the social and economic systems that support them. Today, surviving Damascus swords continue inspiring artists as well as scientists. Museums carefully preserve these blades, not simply because they were effective weapons, but because they represent the highest levels of craftsmanship achieved during their time. Each sword combines engineering precision with artistic beauty in a way that few historical objects can equal. Even after centuries, they continue capturing the imagination of anyone who studies them closely. That enduring fascination comes from the remarkable balance the swords represent. They are both beautiful and practical. They are artistic creations shaped by scientific principles. They emerged through careful experimentation long before the scientific method was formally developed. They remind us that some of humanity's greatest discoveries were made not inside laboratories, but beside glowing furnaces, where patient craftsmen observed nature closely enough to uncover its hidden rules. Every authentic Damascus blade stands as lasting evidence that curiosity, observation, and generations of accumulated experience can accomplish achievements so remarkable that they continue inspiring the world hundreds of years later. Although Damascus steel eventually disappeared as a living craft, its story never truly ended. Instead, it entered a new chapter shaped not by blacksmiths standing beside charcoal forges, but by archaeologists carefully excavating ancient workshops, museum curators preserving surviving blades, and scientists using technologies that the original craftsmen could never have imagined. Every authentic sword that survived the centuries became both a historical artifact and a scientific record, preserving within its steel countless clues about the remarkable knowledge of the people who created it. Rather than fading into legend, the Damascus sword gradually transformed into one of history's most fascinating research projects. Archaeologists searching ancient cities throughout the Middle East and South Asia have uncovered fragments of crucibles, furnace remains, iron slag, unfinished blades, broken tools, and countless other pieces of evidence that help reconstruct the manufacturing process. Even small discoveries contribute valuable information. The chemical composition of furnace walls reveals the temperatures ancient workshops achieved. Fragments of crucibles show how they were constructed and what materials they contained. Tiny pieces of slag preserve evidence of the reactions taking place inside the furnaces more than 1,000 years ago. Each excavation adds another piece to a puzzle, assembled slowly through decades of careful research. Blacksmiths did not simply build a fire wherever convenient. Successful workshops were carefully planned environments where every tool had a purpose. Heavy anvils rested upon solid wooden blocks capable of absorbing repeated hammer blows. Bellows were positioned to supply a steady flow of air into the forge without interfering with the smith's work. Grinding stones stood nearby for shaping and polishing blades, while quenching vessels remained close enough to cool heated steel at precisely the right moment. Researchers have also studied the tools used by these ancient swordsmiths with growing interest. Surprisingly, many appear remarkably simple. Hammers of different sizes shape the steel through thousands of controlled blows. Tongs allowed craftsmen to hold glowing metal safely within the fire. Chisels, punches, files, and grinding stones completed much of the detailed finishing work. None of these tools possess the precision machining found in modern factories, yet when guided by highly skilled hands, they proved capable of producing blades whose quality continues astonishing engineers today. The lesson is both simple and profound. Experimental blacksmiths working today often describe forging steel as a conversation rather than a battle. Every strike of the hammer produces a response from the metal. The steel stretches, thickens, bends, or resists depending upon its temperature and internal condition. A skilled craftsman constantly observes these subtle changes before deciding how to proceed. If the blade begins cooling too quickly, it returns to the fire. If the steel moves exactly as expected, forging continues. This continual exchange between craftsman and material formed the foundation of ancient sword making. Rather than forcing the steel to obey, master smiths learned to recognize its natural behavior and work with it. This philosophy appears repeatedly throughout the history of Damascus steel. Success depended less upon brute force than upon careful control. The charcoal fire had to burn steadily rather than fiercely. The steel needed gradual heating instead of sudden extremes. Hammer blows remained deliberate rather than reckless. Cooling required patience. Polishing advanced through progressively finer abrasives without rushing ahead. At every stage, restraint proved just as important as action. The finest blades emerged because craftsmen understood that remarkable materials often reveal their greatest qualities only when treated with patience. Modern materials engineers recognize this same principle in countless manufacturing processes, whether producing aircraft turbine blades, medical implants, high-performance racing engines, or spacecraft components. Controlling each stage of production remains essential. Small variations in temperature, cooling rates, chemical composition, or mechanical processing can dramatically influence the finished material. Sophisticated computers now assist with many of these tasks, yet the underlying philosophy has changed surprisingly little since the days of the Damascus swordsmiths. Precision comes from understanding the material, not from rushing the process. This is why the story of Damascus steel continues capturing imaginations around the world. It is not simply the story of an extraordinary sword. Long before laboratories, universities, or scientific journals existed, skilled craftsmen quietly discovered principles of metallurgy that continue influencing engineering today. Their greatest achievement was not merely forging beautiful weapons. It was demonstrating that patience, experience, and a willingness to observe the smallest details could unlock secrets hidden deep within the materials of the natural world, creating objects so extraordinary that they continue inspiring wonder nearly 1,000 years after the final hammer blow fell. The disappearance of authentic Damascus steel has fascinated historians for generations because it reminds us that technological knowledge is not always permanent. Modern society often imagines progress as a steady climb in which every discovery builds upon the last, never to be forgotten. History tells a more complicated story. Entire manufacturing techniques have appeared, flourished, and then vanished as civilizations changed. The original Damascus sword became one of history's greatest examples of this phenomenon. The craftsmen who perfected the process eventually disappeared. The trade networks that supplied their remarkable steel collapsed, and the practical knowledge passed from one generation to the next slowly faded until only the finished blades remained to tell their story. Several factors contributed to this gradual disappearance rather than a single dramatic event. The supply of high-quality wootz steel from southern India became increasingly unreliable as political boundaries shifted and regional conflicts disrupted long-established trade routes. At the same time, changes in military technology gradually reduced the importance of swords on the battlefield. Firearms became increasingly common, altering the balance of warfare throughout much of the world. Although beautifully crafted swords continued serving ceremonial purposes and remained symbols of rank and prestige, fewer craftsmen devoted their entire careers to perfecting the extraordinary techniques once required to produce the finest Damascus blades. As demand slowly declined, so too did the opportunity for master swordsmiths to pass their knowledge to future generations. The loss illustrates an important characteristic of traditional craftsmanship. Much of the most valuable knowledge never existed inside books. A master swordsmith might recognize the correct forging temperature by the exact shade of glowing orange reflected across the steel. He could judge the proper rhythm of hammer blows by sound alone, or sense subtle changes in the metal through the resistance transmitted back through the hammer handle. These skills proved extraordinarily difficult to describe with words because they depended upon years of direct experience. This pattern appears throughout the history of technology. Ancient builders created monuments whose construction methods remain debated today. Roman engineers developed concrete capable of surviving for 2,000 years in harsh marine environments. Damascus steel belongs within this remarkable group of achievements, reminding us that knowledge can be surprisingly fragile when it depends entirely upon human memory and apprenticeship, rather than detailed written records. Modern researchers therefore approach surviving Damascus swords with extraordinary respect. Every blade represents an opportunity to recover information that would otherwise remain lost forever. Instead of viewing the swords only as beautiful historical objects, scientists now recognize them as archives of ancient engineering preserved inside metal itself. Every microscopic structure, every trace element, every carbide band, and every grain boundary contains information about the conditions under which the steel was originally created. The sword has become its own historical document, recording its manufacturing process in a language that modern science is only beginning to read. One particularly exciting area of research involves computer modeling. Using advanced software, engineers simulate how carbon atoms move through heated iron, how different cooling rates influence crystal formation, and how trace elements affect the development of carbide networks inside steel. These virtual experiments allow researchers to test countless manufacturing conditions that would require years to reproduce physically inside a forge. By comparing these computer models with the microscopic structures observed in authentic Damascus blades, scientists gradually narrow the range of possible techniques used by the original craftsmen. The process resembles solving an enormous historical puzzle, where every experiment reveals another small piece of the overall picture. Even artificial intelligence has begun contributing to this work. Machine learning systems can analyze enormous collections of microscopic images, comparing patterns that would require human researchers years to examine manually. These systems identify subtle relationships between chemical composition, heat treatment, and crystal structure, helping scientists recognize manufacturing signatures that might otherwise remain hidden. It is a remarkable thought that one of history's oldest metallurgical mysteries is now being investigated with some of the newest technologies ever developed. Ancient craftsmanship and modern computation have become unlikely partners in the search for answers separated by nearly 1,000 years. Yet despite all these remarkable tools, the greatest lesson remains surprisingly simple. The original Damascus sword was never the product of one brilliant invention. It emerged through centuries of gradual refinement involving miners, charcoal makers, crucible builders, merchants, blacksmiths, polishers, and countless apprentices who each contributed another small improvement to the process. That enduring lesson may ultimately prove even more valuable than the legendary steel itself. As historians pieced together the story of Damascus steel, they also began recognizing that the swords represented something much larger than the history of warfare. The legendary blades could never have existed through the efforts of a single kingdom acting alone. Their creation depended upon miners extracting iron ore in southern India, skilled craftsmen producing crucible steel, merchants transporting valuable ingots across deserts and mountains, and master swordsmiths in Damascus transforming those ingots into works of extraordinary engineering. Every completed blade became evidence that cooperation between distant cultures has shaped technological progress throughout human history. The story also challenges many modern assumptions about ancient technology. It is tempting to imagine that people living 1,000 years ago possessed only simple tools and limited scientific understanding. Yet Damascus steel demonstrates that practical knowledge can advance to astonishing levels even without modern theories or laboratory equipment. Ancient craftsmen could not describe atoms, crystal lattices, or carbon diffusion, but they developed manufacturing methods that manipulated all of those phenomena with precision. Their understanding emerged through observation rather than equations, through repeated experimentation rather than formal scientific training. They learned by watching the behavior of the fire, the changing colors of heated steel, the sound of the hammer striking the anvil, and the performance of every finished blade. In many respects, they practiced science long before science acquired its modern vocabulary. This distinction between theoretical knowledge and practical experience remains important today. An engineer may understand the mathematics describing the strength of steel, while an experienced blacksmith often develops an instinctive feel for the material that cannot easily be written into a textbook. Damascus steel illustrates that partnership beautifully. The original swordsmiths mastered practical metallurgy through centuries of experience, while modern scientists continue explaining the microscopic processes that made their remarkable success possible. Neither perspective alone tells the complete story. Together, they reveal one of the finest examples of human ingenuity preserved from the ancient world. The legendary blades have also become valuable teaching tools within universities and research laboratories. Students studying materials science frequently examine Damascus steel when learning how processing influences the properties of metals. They discover that the arrangement of microscopic structures often matters just as much as the chemical composition itself. Two pieces of steel containing nearly identical amounts of carbon can perform very differently if they have been heated, cooled, or forged in different ways. This lesson reaches far beyond sword making. It influences the design of bridges, aircraft, medical implants, power plants, automobiles, spacecraft, and countless other technologies that depend upon carefully engineered materials. Engineers often describe materials as possessing a memory of how they were made. Every manufacturing step leaves subtle traces hidden inside the finished object. Rolling, forging, welding, heat treating, and cooling all reshape the internal arrangement of atoms and crystals in ways that remain detectable long afterward. Damascus steel provides one of history's clearest demonstrations of this principle. The flowing patterns visible across each blade are not decorations added at the end of production. They are permanent records of the steel's entire history, preserving evidence of its creation from the moment the original wootz ingot cooled inside its clay crucible until the final polishing revealed the remarkable structures hidden beneath the surface. The swords therefore remind us that every manufactured object carries a story. A modern airplane wing reflects decades of research in metallurgy, aerodynamics, and precision manufacturing. A surgical instrument embodies advances in stainless steel, machining, and sterilization. In much the same way, an authentic Damascus sword preserves the accumulated discoveries of ancient miners, charcoal makers, furnace builders, merchants, and master blacksmiths whose combined efforts gradually produced one of the world's most admired materials. Looking closely at the blade is like reading a historical record, written not with ink upon paper, but with carbon, iron, and heat locked forever inside the steel itself. This explains why Damascus steel continues inspiring such admiration among scientists as well as historians. It reminds us that technological excellence is rarely the result of a single invention or one brilliant individual. Every craftsman inherited lessons from those who came before, while adding new insights for those who followed. The Damascus sword therefore stands not only as a masterpiece of metallurgy, but also as a monument to humanity's remarkable ability to learn patiently from the natural world, one observation at a time. One reason the Damascus sword continues captivating people today is that it represents a rare moment in history when beauty and engineering became inseparable. The finest Damascus blades accomplished both goals at once. They served as practical weapons capable of extraordinary performance, yet they also displayed flowing patterns of remarkable elegance that made every sword visually unique. The same microscopic structures responsible for the blade's famous appearance also contributed to its exceptional mechanical properties, meaning that its beauty was not added afterward, but emerged naturally from the science hidden within the steel itself. This relationship between appearance and function continues influencing modern engineering. Designers often strive to create products that are both efficient and visually appealing, whether building high-speed trains, aircraft, bridges, or advanced medical equipment. The Damascus sword achieved this balance centuries before industrial design became an academic discipline. Every graceful curve along the blade served a practical purpose. Its carefully shaped edge optimized cutting performance, its balanced weight improved handling, and its flowing surface patterns reflected the remarkable internal structure created through craftsmanship. It stands as a reminder that exceptional engineering often possesses a quiet elegance all its own. Collectors who examine authentic Damascus swords frequently notice another remarkable characteristic. No two blades are exactly alike. Although they followed the same general principles of manufacture, each sword developed its own distinctive pattern during the slow cooling of the original wootz ingot and the careful forging that followed. Some display broad flowing waves, while others reveal tighter ripples, delicate ladders, or intricate swirling designs stretching from the base of the blade to its finely sharpened tip. Modern scientists understand that these variations resulted from tiny differences in carbon distribution, cooling rates, trace elements, and forging techniques. To the ancient craftsmen, however, each blade simply possessed its own individual character, shaped by the unique behavior of the steel itself. This individuality makes authentic Damascus swords especially valuable to researchers because every surviving blade provides slightly different information. One sword may preserve unusually large carbide bands, while another reveals distinctive grain structures or trace element concentrations that offer additional clues about the original manufacturing process. Instead of studying a single perfect example, scientists compared dozens of surviving blades from different periods and regions, gradually building a more complete understanding of how the technology evolved over time. Each sword contributes another chapter to a much larger historical story that continues unfolding with every new discovery. The preservation of these remarkable weapons has therefore become an international effort involving museums, universities, conservation laboratories, and private collections across the world. Institutions carefully document every visible feature before examining the blades with non-destructive imaging techniques that reveal hidden details without damaging the priceless artifacts. Three-dimensional scanning captures the exact geometry of each sword, while advanced spectroscopy identifies its chemical composition, and microscopic imaging records the internal structures preserved beneath the polished surface. Future generations of researchers will likely possess even more powerful technologies, allowing them to uncover details that remain invisible today, just as electron microscopes once revealed structures unimaginable only a century ago. The story of Damascus steel also reminds us that history is rarely as isolated as it first appears. Ancient civilizations did not develop entirely independently from one another. Ideas, materials, and technologies constantly traveled alongside merchants, explorers, diplomats, and travelers moving across continents. The remarkable crucible steel developed in southern India eventually reached Damascus through trade. Knowledge of exceptional swords spread into Europe through commerce and warfare. Modern scientific research now brings together specialists from universities across many different countries, each contributing new insights into a mystery first created nearly 1,000 years ago. Across every era, cooperation has remained one of the most powerful forces driving human innovation. Standing before an authentic Damascus blade today, it is easy to admire its graceful lines and shimmering patterns without fully appreciating the extraordinary journey hidden within the steel. The iron first formed deep inside the earth billions of years before human civilization existed. Ancient miners uncovered the ore, skilled craftsmen transformed it into remarkable crucible steel, merchants carried it across thousands of miles of rugged landscape, and master swordsmiths patiently shaped it into one of history's greatest engineering achievements. Centuries later, scientists continue examining the same blade beneath microscopes, powerful enough to reveal structures measured in millionths of a meter. Few objects connect such immense spans of time so seamlessly, linking the birth of our planet with the latest advances in modern materials, science, through a single piece of carefully forged steel. The influence of Damascus steel reaches even into the language we use today. The word steel often brings to mind strength, resilience, and reliability, while the name Damascus has become almost synonymous with exceptional craftsmanship. Although many people recognize the term without knowing its full history, the reputation built by these remarkable blades has endured for centuries. Few manufactured objects have become so closely associated with excellence that their very name evolves into a symbol of quality. It is also remarkable how many different scientific disciplines now contribute to understanding a single historical object. Geologists study the mineral deposits that supplied the original iron ore. Chemists analyze the composition of the steel and identify trace elements hidden within it. Physicists investigate crystal structures using X-rays and electron diffraction. Archaeologists excavate ancient workshops and reconstruct forgotten manufacturing techniques. Historians examine trade records and written accounts describing the movement of steel across continents. Engineers recreate historical furnaces, while materials scientists compare ancient blades with modern alloys. Each discipline contributes another piece of the puzzle, demonstrating that even one sword can become the meeting point for an astonishing range of human knowledge. The story also illustrates the remarkable patience required for true craftsmanship. Modern manufacturing often emphasizes speed, automation, and efficiency, producing thousands of identical parts every hour. The creation of an authentic Damascus blade followed an entirely different philosophy. Every stage unfolded according to the behavior of the material rather than the demands of a schedule. The charcoal burned until the proper temperature was reached. The steel remained in the fire until it responded correctly beneath the hammer. Cooling proceeded at the pace required by the metal itself. Polishing advanced through increasingly finer abrasives without skipping steps. Nothing could be rushed without risking the quality of the finished blade. In many respects, the steel itself determined the rhythm of the work. That patient approach offers an interesting contrast with many modern technologies. Computers perform billions of calculations every second. Factories produce enormous quantities of steel each day, and automated machines manufacture components with astonishing precision. Yet despite these incredible advances, many of the highest quality products in the modern world still depend upon skilled craftspeople who understand their materials through years of direct experience. Damascus steel belongs within this long tradition, reminding us that the finest results often emerge when technical knowledge is guided by experienced hands. The swords also encourage us to think differently about innovation itself. Genuine breakthroughs rarely appear fully formed in a single generation. More often they emerge through countless small improvements, accumulated over long periods of time. Every blacksmith who discovered a slightly better forging temperature, every crucible maker who produced a stronger vessel, every merchant who established a more reliable trade route, and every apprentice who mastered another difficult skill contributed to a process that gradually transformed ordinary iron into legendary steel. Progress was measured not in dramatic leaps, but in thousands of careful refinements repeated across centuries. This steady accumulation of knowledge explains why the Damascus sword continues inspiring engineers today. Modern aircraft, spacecraft, medical devices, and advanced materials all reflect the same principle. The Damascus sword simply tells that timeless story in one of its most elegant forms. Looking across the entire history of these extraordinary blades, from the ancient iron ores buried beneath the earth to the bustling workshops of Damascus and the laboratories of the modern world, one theme appears again and again. Curiosity drove every stage of the journey. Someone wondered whether strange rocks might contain useful metal. Someone experimented with hotter furnaces. Someone discovered that carbon transformed iron into steel. Someone patiently forged a crucible ingot instead of an ordinary bloom. Someone noticed that careful heat treatment produced stronger blades. Centuries later, scientists asked new questions beneath powerful microscopes, continuing the same tradition of curiosity that began beside ancient charcoal fires. Across nearly 1,000 years, that desire to understand the natural world has remained the true secret behind the legend of Damascus steel. As researchers continue uncovering new evidence, the story of Damascus steel becomes less about discovering one lost secret and more about appreciating an extraordinary chain of knowledge stretching across centuries. Every new study reinforces the idea that these legendary blades were never the result of a single miraculous ingredient or one revolutionary invention. Instead, they represented the successful combination of geology, chemistry, metallurgy, trade, craftsmanship, and generations of observation. Remove any one of those elements, and the legend might never have existed. Even the landscape itself played an essential role. The iron ore found in southern India contained subtle chemical characteristics that differed from deposits elsewhere in the world. The surrounding forests supplied hardwoods capable of producing high-quality charcoal, while local potters crafted clay crucibles strong enough to survive temperatures that would destroy ordinary pottery. Rivers carried materials between communities, and established trade routes linked inland workshops with busy coastal ports where merchants prepared valuable cargo for the long journey westward. Long before the first hammer struck glowing steel in Damascus, nature and geography had already shaped much of the blade's future. The merchants who transported those precious ingots rarely received the same attention as the famous swordsmiths, yet without them, the story would have ended before it truly began. Their caravans crossed scorching deserts where daytime temperatures climbed relentlessly before giving way to surprisingly cold nights beneath clear skies. They navigated rugged mountain passes, crossed broad rivers, negotiated with local rulers, and protected valuable cargo from thieves along dangerous stretches of road. Every successful journey demanded planning, patience, and remarkable endurance. Each ingot arriving safely in Damascus represented months of travel across thousands of miles, connecting distant civilizations through commerce long before modern transportation existed. Within Damascus itself, the arrival of a new shipment of wootz steel must have been an exciting moment for the city's master swordsmiths. They understood the rarity of the material they held in their hands. Each ingot carried the potential to become an exceptional blade, but only if treated with absolute care. There could be no wasted steel, no careless overheating, and no unnecessary hammer blows. Every stage demanded complete concentration because replacing the material was neither easy nor inexpensive. This scarcity encouraged extraordinary discipline inside the workshop. Swordsmiths learned to use every piece of steel wisely, carefully planning each stage before beginning work. Apprentices observed silently, while masters demonstrated techniques refined over decades of experience. Mistakes became valuable lessons because each error carried real consequences. The forge became both a workplace and a school, preserving skills that survived only because experienced craftsmen patiently taught those willing to learn. Modern educators often emphasize the importance of hands-on learning, and the Damascus sword offers one of history's finest examples of that principle. Reading about forging can explain the general process, but it cannot fully communicate how heated steel feels beneath a hammer, how charcoal sounds as air flows through the bellows, or how the color of glowing metal changes just before it reaches the proper forging temperature. Those lessons emerge only through direct experience. The greatest swordsmiths developed a deep familiarity with their materials that no written description could ever completely capture. That is why authentic Damascus steel continues earning such respect among modern blacksmiths. Even with today's advanced equipment, experienced craftsmen recognize the extraordinary level of skill required to produce those legendary blades consistently. They understand that every successful sword reflected years of disciplined practice rather than isolated moments of inspiration. The ancient masters were not performing mysterious magic. They were applying an exceptional understanding of heat, steel, timing, and craftsmanship developed patiently over entire lifetimes. That realization makes their achievements no less remarkable. The remarkable legacy of Damascus steel also reminds us that history is filled with achievements that were never intended to become mysteries. The craftsmen who forged these legendary blades were not trying to create puzzles for future generations. They were simply producing the finest swords they knew how to make, relying upon techniques refined through centuries of observation and practice. To them, the work was part of everyday life. Each successful blade represented another day's labor inside a familiar workshop, another lesson shared with an apprentice, and another contribution to a tradition that seemed likely to continue indefinitely. No one could have imagined that centuries later, scientists equipped with electron microscopes and advanced laboratories would still be studying the steel they left behind. This perspective offers an important reminder about the way knowledge is preserved. The Damascus sword became one of the world's most famous examples of this fragile relationship between knowledge and time. Its secrets were never intentionally hidden. They simply became more difficult to recover as the people who understood them gradually disappeared. Fortunately, the blades themselves continued telling part of the story. Every authentic Damascus sword became a silent witness to its own creation, preserving clues that remained hidden until science finally developed the tools capable of revealing them. Unlike written records that can burn, decay, or disappear, the steel retained evidence of every stage in its manufacture. The distribution of carbon, the arrangement of microscopic carbides, the size of individual crystals, and the presence of trace elements all remained locked within the blade, patiently waiting for future generations to discover their meaning. In that sense, every surviving sword became both an artifact and an archive, recording its own history within the structure of the metal itself. Researchers often describe these investigations as conversations across time. The ancient swordsmiths cannot answer questions directly, yet the steel responds through careful scientific examination. Every microscopic image, every chemical analysis, and every experimental reconstruction allows modern scientists to ask another question and receive another small piece of the answer. Although the original craftsmen never intended to communicate with people living hundreds of years in the future, their work continues speaking through the remarkable material they created. Few historical objects possess the ability to teach us so much, long after the hands that shaped them have disappeared. The Damascus sword also demonstrates that technological innovation rarely belongs to one culture alone. Too often, history is simplified into stories of isolated civilizations making discoveries independently. The truth is usually far more interconnected. The iron came from one region, crucible steel developed in another, merchants carried the material across continents, and master swordsmiths refined it into legendary blades elsewhere. Knowledge flowed continuously alongside trade, diplomacy, exploration, and cultural exchange. The Damascus sword therefore stands as a reminder that many of humanity's greatest achievements emerge through cooperation rather than isolation, with countless individuals contributing their expertise across great distances and many generations. That is why these remarkable blades continue inspiring people from so many different fields today. Historians admire the civilizations that produced them. Archaeologists study the workshops where they were forged. Chemists analyze their composition. Engineers examine their mechanical properties. Blacksmiths attempt to recreate their remarkable qualities. Artists appreciate the flowing beauty of their surfaces, while museum visitors simply pause to admire the quiet elegance of a sword whose story stretches across nearly 1,000 years. Very few objects possess the ability to connect so many different disciplines while continuing to reveal new discoveries with each passing generation. Looking closely at an authentic Damascus blade, its greatest achievement was never simply its ability to cut. Its true significance lies in everything the steel represents. Within that single piece of metal rests the history of ancient geology, the chemistry of iron and carbon, the patience of generations of craftsmen, the courage of merchants crossing continents, the rise and fall of great civilizations, and the remarkable human desire to understand the materials of the natural world. Every ripple visible across its polished surface tells part of that story, preserving within graceful flowing lines one of the greatest engineering accomplishments of the ancient world. One of the most enduring lessons hidden within the story of Damascus steel is that true mastery often develops so gradually that the people living through it scarcely notice. No single blacksmith woke one morning having suddenly invented the perfect sword. A slightly hotter furnace, a more reliable source of charcoal, a better understanding of when to strike the steel, a more careful approach to cooling, or a subtle refinement in polishing might seem insignificant on its own. Yet over hundreds of years, these countless small improvements accumulated into one of the greatest achievements in the history of metallurgy. The Damascus sword reminds us that remarkable innovations are often built from thousands of patient observations rather than one dramatic breakthrough. This gradual process closely resembles evolution within the natural world. Successful techniques survive because they consistently produce better results, while unsuccessful methods quietly disappear. Ancient swordsmiths may not have understood the scientific principles behind every decision they made, but they understood results. If one approach created a stronger blade, they repeated it. If another caused cracks or weak edges, they abandoned it. Over centuries, this practical form of experimentation became one of humanity's most powerful tools for advancing technology. The craftsmen who produced Damascus steel were among history's greatest practitioners of empirical science. They observed relationships between fire, metal, charcoal, and cooling with precision, recording those lessons not in scientific journals, but in the routines of everyday work. Every successful blade became another experiment, confirming what experience had already suggested. Their workshops functioned as laboratories, their furnaces served as research equipment, and every completed sword represented the latest results of investigations that had continued across many generations. The more researchers learn about Damascus steel, the more respect they develop for the remarkable sophistication of those ancient craftsmen. Modern laboratories possess tools capable of measuring temperatures to fractions of a degree, identifying trace elements at astonishingly small concentrations, and imaging structures invisible to the naked eye. Yet despite all these advantages, reproducing the finest historical Damascus blades remains an enormous challenge. This is not because modern scientists lack intelligence or technology. The story also reminds us that some of humanity's greatest discoveries emerge when curiosity meets patience. The original swordsmiths did not rush their work. They allowed the steel to reveal its own behavior, carefully adjusting each stage of the process in response to what they observed. Every decision respected the material itself. Heat could not be hurried. Cooling followed its own natural pace. Forging demanded rhythm rather than force. Even the beautiful flowing patterns remained hidden until polishing and gentle etching finally revealed what had been quietly forming inside the steel all along. Looking back across nearly 1,000 years of history, it becomes remarkable how completely Damascus steel reflects the partnership between humanity and the natural world. The iron originated deep within the earth billions of years before human civilization existed. Forests provided the charcoal that fueled the furnaces. Clay from riverbanks became crucibles capable of containing molten steel. Carbon from burned wood transformed ordinary iron into exceptional material. Human ingenuity never replaced these natural processes. Few achievements demonstrate more clearly that some of our greatest technologies arise not from conquering nature, but from understanding it deeply enough to work alongside it. As the story of Damascus steel approaches its final chapters, one idea continues rising above all the others. The legendary blades were never the achievement of a single person working alone. They represented the combined efforts of miners, charcoal makers, potters, merchants, furnace builders, blacksmiths, polishers, traders, and apprentices spread across thousands of miles and hundreds of years. The finished sword, therefore, became far more than a weapon. Today, that same spirit of collaboration continues inside research laboratories around the world. Metallurgists compare notes with archaeologists. Historians work alongside chemists. Engineers consult museum conservators, while experimental blacksmiths recreate ancient furnaces to test theories suggested by microscopic analysis. It is fitting that solving the mystery of Damascus steel now requires the same kind of knowledge that originally created it. The story also offers an unexpected lesson about innovation itself. Modern society often celebrates dramatic inventions and sudden breakthroughs, but Damascus steel reminds us that lasting achievements are usually built much more slowly. Progress emerged through patience rather than speed, through refinement rather than revolution. That quiet process transformed ordinary iron into one of the most celebrated materials in history, without any single moment when someone could point to one discovery and say, "Everything changed today." Even after centuries of scientific investigation, authentic Damascus swords continue rewarding those who look closely. A casual observer sees a beautifully polished blade decorated with graceful flowing lines. A historian recognizes evidence of ancient trade routes linking distant civilizations. A blacksmith notices subtle clues left behind by the hammer and forge. A materials scientist sees intricate carbide networks and controlled crystal structures hidden beneath the polished surface. Each perspective reveals another layer of understanding, proving that the finest creations often become richer and more fascinating the more carefully they are studied. That is why these remarkable blades continue capturing imaginations after nearly 1,000 years. They remind us that knowledge is one of humanity's greatest treasures, yet also one of its most fragile. At the same time, curiosity has an equally remarkable power. Even after centuries of forgotten techniques and vanished workshops, people continued asking questions, examining the evidence, and searching for answers until the story slowly began revealing itself once again. The Damascus sword therefore stands not only as a masterpiece of ancient engineering, but also as a celebration of humanity's endless desire to learn. Standing at the end of this remarkable journey, from the fiery birth of iron deep within the earth billions of years ago, to the glowing forges of medieval Damascus and the advanced research laboratories of today, the greatest secret of Damascus steel was never hidden inside the blade alone. Its true secret was the patient partnership between nature and human ingenuity. Iron, carbon, heat, time, observation, and craftsmanship all work together to produce something no single element could have achieved by itself. The legendary sword became the final expression of that partnership, preserving within its graceful flowing patterns one of history's greatest examples of science, engineering, and craftsmanship united in perfect balance. Although the finest Damascus swords have become priceless historical artifacts, their greatest value today is no longer measured by their usefulness in battle. Every surviving blade bridges two very different worlds. One belongs to ancient blacksmiths working beside charcoal fires, judging temperature by the color of glowing steel and relying entirely upon practiced experience. The other belongs to modern laboratories filled with electron microscopes, X-ray scanners, supercomputers, and sophisticated analytical instruments capable of examining structures measured in billionths of a meter. Despite the centuries separating them, both worlds are connected by the same desire to understand the remarkable behavior of iron, carbon, and heat. That connection explains why Damascus steel continues inspiring engineers and scientists today. They worked with the properties of steel instead of fighting against them, carefully guiding each stage of the process until the material revealed its greatest strengths. Modern engineering often follows the same philosophy. Whether designing lighter aircraft, stronger bridges, more efficient engines, or advanced medical implants, engineers begin by understanding how materials behave before deciding how best to shape them. The tools have changed dramatically, but the underlying principle remains remarkably familiar. The Damascus sword also reminds us that scientific discovery rarely reaches a final destination. Every generation believes it has answered the most important questions, only for new technologies to reveal mysteries that earlier researchers never imagined. Historians once thought the flowing patterns were simply decorative. Later, scientists discovered they reflected microscopic carbide structures hidden inside the steel. More advanced instruments revealed the influence of trace elements and controlled cooling rates. The story continues evolving because every new generation possesses better tools with which to ask deeper questions. In that sense, the Damascus sword has never truly stopped being made. Although the original workshops have long since disappeared, every new experiment, every archaeological excavation, every microscopic image, and every carefully forged reproduction adds another chapter to its remarkable history. The same desire to understand the natural world that guided ancient swordsmiths beside their glowing forges continues guiding modern researchers inside laboratories around the globe. Looking across the entire journey, from iron forming deep within the young earth billions of years ago, to the bustling trade routes linking India with Damascus, from patient craftsmen shaping glowing steel beneath the rhythm of the hammer, to scientists examining the finished blades beneath powerful microscopes, one truth becomes wonderfully clear. The legend of Damascus steel was never built upon magic or myth. That quiet pursuit of knowledge became the true edge hidden inside every legendary blade, and it remains every bit as inspiring today as it was nearly 1,000 years ago. For all of its scientific importance, the most remarkable aspect of Damascus steel is that it never lost its sense of wonder. Historians admire the civilizations that produced it. Archaeologists value the clues preserved within every surviving blade. Engineers study its remarkable mechanical properties, while blacksmiths respect the extraordinary skill required to forge it successfully. Museum visitors, however, often experience something much simpler. Standing before an authentic Damascus sword, they pause in quiet admiration. Light moves gently across the polished steel, revealing graceful waves that seem almost alive beneath the surface. Few people understand every detail of the metallurgy hidden inside the blade, yet almost everyone immediately recognizes that they are looking at something truly exceptional. That quiet sense of wonder has followed Damascus steel throughout its entire history. Merchants crossing deserts carefully protected valuable ingots because they understood their rarity. Apprentices watched experienced masters with complete attention, hoping to absorb even the smallest lesson. Warriors carried these blades with enormous pride, while rulers often presented them as gifts worthy of kings and ambassadors. Although the reasons have changed over time, admiration for the craftsmanship itself has remained remarkably constant. The legendary Damascus sword depended upon discoveries made by countless people who never met one another. Miners uncovered valuable iron ore. Potters crafted crucibles capable of surviving intense heat. Charcoal makers prepared the fuel that powered the furnaces. Skilled metallurgists created exceptional wootz steel in southern India. Merchants carried those precious ingots across mountains, deserts, and rivers until they reached Damascus. There, master swordsmiths transformed them into legendary blades whose reputation spread throughout the medieval world. As we continue advancing into an age of increasingly sophisticated technology, Damascus steel offers a lesson that feels just as relevant today as it did centuries ago. The greatest innovations are rarely created through speed alone. Ancient swordsmiths never imagined that people living hundreds of years in the future would still be studying their work. Yet every carefully forged blade continues teaching new generations about metallurgy, engineering, craftsmanship, and the remarkable possibilities hidden inside ordinary materials. In that sense, the Damascus sword remains exactly what it has always been, not simply a masterpiece of steel, but a timeless celebration of human curiosity and the enduring pursuit of knowledge. The remarkable journey of Damascus steel also encourages us to think about the relationship between discovery and preservation. In the case of Damascus steel, enough blades survived to allow future generations to study them, but countless workshops, furnaces, tools, and written records have long since vanished. Archaeologists continue uncovering fragments buried beneath layers of soil, while historians search old manuscripts for even the briefest descriptions that might explain another step in the manufacturing process. Every discovery reminds us that preserving the achievements of earlier civilizations is just as important as creating new ones. Museums now play an essential role in that effort. Behind controlled glass displays, authentic Damascus swords rest under lighting designed to protect the steel, while allowing visitors to appreciate the graceful patterns flowing across each blade. Temperature and humidity remain carefully regulated because even small environmental changes can encourage corrosion over long periods of time. Conservators inspect every sword regularly, using specialized techniques to remove contaminants without disturbing the original surface. Their work is intentionally quiet and often goes unnoticed, yet it ensures that these remarkable artifacts remain available for future generations of researchers, students, and visitors who wish to understand one of history's greatest metallurgical achievements. Education has become another important part of the sword's modern legacy. Universities around the world use Damascus steel as an example when teaching metallurgy, engineering, archaeology, chemistry, and material science. Students examining these ancient blades quickly discover that history and science are not separate subjects, but deeply connected ways of understanding the world. A single sword can illustrate geological processes that formed iron ore billions of years ago, chemical reactions inside ancient furnaces, trade networks linking distant civilizations, and microscopic crystal structures that continue influencing modern engineering. Few historical objects demonstrate so many different scientific principles at once. The Damascus sword has also inspired a renewed appreciation for traditional craftsmanship. Blacksmiths, woodworkers, potters, glassblowers, and other artisans continue practicing techniques that require years of dedication to master. It is about developing a deep understanding of materials and learning how to reveal their finest qualities through careful attention rather than unnecessary force. The ancient swordsmiths of Damascus embodied that philosophy in every blade they produced. This is why the legend has never faded. Every generation finds something different to admire. Medieval warriors respected the sword's performance. Merchants valued its rarity. Kings prized its beauty. Historians appreciate its place in the story of civilization. Scientists marvel at the sophisticated metallurgy hidden within its polished surface. Engineers study the relationship between microscopic structure and mechanical performance. Artists admire the flowing patterns that make every blade unique. The Damascus sword continues speaking to each generation in a different way, proving that truly exceptional achievements possess a timeless quality that extends far beyond the era in which they were created. The greatest mystery surrounding Damascus steel was never whether modern science could eventually explain its remarkable structure. The greater mystery is how generations of craftsmen, working without microscopes, computers, or modern laboratories, developed such an extraordinary understanding of their material through observation alone. Their success reminds us that careful attention, patience, and a willingness to learn from nature can accomplish achievements that endure for centuries. It is a lesson written not in books or formulas, but in the graceful, flowing lines preserved forever within one of history's most celebrated blades. The story of Damascus steel ultimately reminds us that the greatest achievements in human history are often those that continue teaching long after their original purpose has faded. The legendary blades were created to serve warriors, protect kingdoms, and demonstrate the extraordinary skill of their makers. Centuries later, they now serve an entirely different purpose. They have become teachers. Every surviving sword offers another lesson about metallurgy, engineering, craftsmanship, international trade, archaeology, and the remarkable ability of human beings to solve difficult problems through patience and observation. Looking back across the centuries, it is remarkable how many different people unknowingly contributed to the creation of a single Damascus blade. Deep beneath the earth, geological forces concentrated the iron ore millions of years before humans existed. Forests slowly grew, providing the hardwood that would eventually become charcoal. Potters refined their skills until they could produce crucibles capable of surviving intense heat. Miners uncovered valuable ores, while metalworkers patiently experimented with new techniques. Merchants carried precious ingots across deserts, rivers, and mountain ranges, linking civilizations separated by thousands of miles. Finally, master swordsmiths combined all of those contributions into blades whose reputation would outlive every kingdom that helped create them. The Damascus sword was never simply the achievement of one craftsman. That is why these remarkable blades continue inspiring such admiration today. They demonstrate that knowledge grows most powerfully when it is shared, preserved, and refined over time. Modern scientists continue following exactly the same path. The chain of learning has never truly been broken. it has simply continued in a different form. Standing at the end of this remarkable journey, from the fiery birth of iron deep within the young earth, to the bustling markets of medieval Damascus and the sophisticated laboratories of the modern world, one truth becomes wonderfully clear. The legend of Damascus steel was never created by mystery alone. It was created by curiosity. Curiosity led ancient people to wonder whether strange rocks might contain useful metal. Curiosity inspired craftsmen to experiment with hotter furnaces and new forging techniques. Curiosity encouraged merchants to carry valuable materials across continents and scientists to examine surviving blades beneath powerful microscopes hundreds of years later. Across every chapter of the story, curiosity remained the sharpest tool of all. It transformed ordinary iron into extraordinary steel, preserved the lessons of forgotten craftsmen, and continues guiding new generations toward a deeper understanding of one of history's greatest engineering achievements. Long after the last authentic Damascus sword left the forge, its greatest contribution to history continued unfolding in ways its makers could never have imagined. The blades became lasting evidence that knowledge does not belong to any single generation. Every discovery made by the ancient swordsmiths eventually became part of a much larger human story, inspiring blacksmiths, scientists, engineers, historians, archaeologists, and students separated by centuries, yet connected by the same desire to understand how remarkable things are created. The glowing furnaces of medieval Damascus may have gone cold, but the questions first raised beside those fires continue burning brightly today. That is the greatest legacy of Damascus steel. It reminds us that the pursuit of knowledge is never truly finished. Every answer leads naturally to another question, and every generation inherits both the discoveries and the mysteries left behind by those who came before. Ancient craftsmen spent their lives refining the behavior of iron and carbon without ever knowing the microscopic structures hidden inside the steel. Modern researchers can now observe those structures directly, yet they continue uncovering new details that inspire fresh investigations. The journey from curiosity to understanding has never reached an ending. It simply continues, carried forward by each new generation, willing to look a little closer than the last. The Damascus sword also stands as a remarkable example of how science and craftsmanship have always belonged together. Today, we often separate engineering from art, chemistry from creativity, and research from skilled manual work. The master swordsmiths never saw those boundaries. Every strike of the hammer reflected both artistic judgment and practical engineering. Every adjustment to the forge relied upon observation of natural processes. Every finished blade united mathematics hidden within geometry, chemistry hidden within steel, physics hidden within heat, and beauty revealed across the flowing surface. Long before these subjects became separate academic disciplines, they existed together inside every Damascus sword. Even now, when modern blacksmiths light their forges and heat steel until it glows with familiar shades of red, orange, and yellow, they participate in a tradition stretching back thousands of years. The equipment may be more refined, safety standards may be higher, and scientific understanding may be vastly greater, but the essential relationship between craftsman and material remains wonderfully familiar. Steel still responds to heat. Carbon still transforms iron. Careful timing still matters. Patience still produces better results than haste. In that sense, the ancient masters continue teaching every time a new blade begins taking shape beneath the rhythm of the hammer. Looking across the entire history of Damascus steel, it becomes impossible to separate the sword from the people who created it. Behind every surviving blade stand miners who uncovered ancient ore, charcoal makers who patiently tended slow-burning fires, potters who shaped crucibles from simple clay, merchants who crossed continents carrying valuable cargo, apprentices who devoted years to mastering difficult skills, and master swordsmiths whose knowledge represented the accumulated experience of countless generations. Together, they accomplished something extraordinary, creating blades whose reputation endured long after the kingdoms that commissioned them had disappeared into history. And that is the quiet lesson these remarkable swords continue offering today. The greatest achievements are rarely built through speed or shortcuts. Damascus steel was never simply forged inside a furnace. It was forged through centuries of curiosity, discipline, cooperation, and knowledge, each generation adding another careful layer until ordinary iron became one of the most admired materials the world has ever known. That enduring spirit of discovery remains the sharpest edge ever carried within a Damascus blade. As our journey through the secret chemistry of forging legendary Damascus steel slowly comes to an end, these remarkable blades were never defined by sharpness alone. Iron formed deep within the earth billions of years before the first blacksmith ever lit a forge. Carbon, hidden within ordinary pieces of charcoal, quietly transformed that iron into steel. Every sword became the final expression of countless discoveries made across centuries, proving that some of humanity's greatest achievements are not created in a single moment, but patiently shaped over many lifetimes. That is the greatest lesson hidden within the flowing patterns of Damascus steel. The original craftsmen never knew about atoms, crystal structures, carbides, or electron microscopes. Instead, they relied upon something equally powerful. Today, nearly 1,000 years later, the surviving blades continue teaching us. Historians read them as records of ancient civilizations and global trade. Archaeologists uncover new clues from forgotten workshops buried beneath the earth. Materials scientists examine microscopic structures that remained hidden for centuries. Engineers study the remarkable relationship between chemistry, heat, and mechanical performance, while modern blacksmiths continue honoring the traditions of the craftsmen who first transformed simple iron into legendary steel. Every generation adds another layer of understanding, proving that the story of Damascus steel did not end when the last authentic blade left the forge. It continues every time someone asks another question, performs another experiment, or pauses to admire the extraordinary knowledge preserved within a single piece of carefully forged metal. Looking back across our entire journey, from the violent birth of the earth more than 4.5 billion years ago, to the rich iron ores of southern India, the bustling caravan routes that crossed Asia, the crowded markets of Damascus, the glowing charcoal forges of master swordsmiths, and the advanced research laboratories of today, one remarkable truth quietly connects every chapter. Curiosity has always been humanity's greatest tool. It inspired miners to search beneath the earth, craftsmen to experiment with fire and steel, merchants to carry knowledge across continents, and scientists to continue exploring mysteries that have endured for centuries. The legendary Damascus sword stands as a timeless reminder that when curiosity is joined with patience, observation, and generations of knowledge, ordinary materials can become extraordinary achievements whose influence reaches far beyond their own time. Thank you for joining me on tonight's journey through the secret chemistry of forging legendary Damascus steel swords. If you enjoyed this peaceful exploration through history, science, engineering, and ancient craftsmanship, I'd love for you to subscribe and join us again. New sleep stories are posted every other day, and you'll find many more relaxing journeys waiting for you in our growing collection of playlists. Until next time, sleep well, dream peacefully, and I'll see you in the next story.